Okay, so picking back up where we left off, we had evaluated the three-factor model, the four-factor model, and despite the fact that quantitatively a four-factor model seemed to fit a little bit better, uh, there was good evidence that a three-factor model was the best or most parsimonious model for the data that we've got. In addition, let's just say it, the three-factor model mapped onto our theory. When we're constructing items for any type of measure, our goal is to construct the best items possible that are trying to tap into this underlying theta, this underlying factor, right? And so one of the questions that you have to ask yourself when you're constructing items for a new measure is, does this item really seem to be tapping into the factor that I think it's tapping into? And all of that winds up being, some of it at least, winds up being guesswork. And so sometimes we wind up with a bad item. And I think that one of those items is just not a great item. What item was it? Do we remember? It's right there, I guess. It's item 3. Let's scroll up to the three-factor model, and let's see how item 3 fit here. That's the standard error. Item 3 actually fits pretty good on this one factor with all's 1 and all's 5. All's 4 is not very good. Somebody want to grab a pencil, and let's do something here quick. Let's figure out which one of these factors each item should load onto. Because in a second, we're going to do a confirmatory factor analysis. One of the problems with this is the model fit that we have seems fantastic or whatever, right? But it's actually allowing every single item to be predicted by every factor that we've got. And in a confirmatory factor analysis, we don't do that, right? We say like this item is specific to this factor. And so we're going to cut out a whole bunch of degrees of freedom because we're going to lose a bunch of these lines, right? For every one of these up here, we've got 17 lines. But if only 3 items are driving that first factor up there, we drop off, 16 lines. Does that make sense? So, or 16 paths. So we're going to figure out what items need to go with this factor, with each factor, and then we're going to redo this as a confirmatory factor analysis. And then we're going to walk through the steps of making this confirmatory factor analysis or testing this confirmatory factor analysis against a couple of other factor structures that are not exploratory but have been hypothesized. So the first step here is to identify which items go on which factors. So the first item goes on which factor? What are we going to say? I would say factor 1 as well. Let's throw it on factor 1. Second item, somebody's writing this down, right? Because we're going to have to go back and add these. We're going to have to make this model. Second item loads on factor 3, very clearly. Third item loads on factor 1. Fourth item loads on factor 2. Fifth item loads on factor 1. Sixth, 1. Seventh, 1. Eighth, 2. And we'll come back to that. Ninth, 2. 10th, 10, 3. 11, 2. 12, 3. 13, 3. 14, 2. 15, 16, 17, and 18. Okay, how many items do we have on factor 1? Count them up for me. Somebody, whoever wrote them down? We have 5. How many items do we have on factor 2? And on factor 3, by process of elimination, we should have 8, right? Now we have some items that actually, like item 4, right? It doesn't load the highest on 2, and it also has a pretty high cross-loading on 4. We have another item down below, item 8, which has a pretty high cross-loading on 1 and a cross-loading on 2, or I mean a primary loading on 2. How are we going to handle this when we get to the confirmatory analysis? That's a possibility. What's another possibility? force it to be on 2. We could do that. We could put it on both. We could cross-load it. What is there are 2 possible reasons why something would cross-load on a factor. The first is that factor is driving responses on that, right?
There's like a higher order
factor. I'm sorry. So I should have said 3. There's a possibility of a higher order factor, right? And then there's this other possibility, which is the bane of our existence when it comes to item construction and confirmatory factor analysis, and that is method variance, right? Like error variance that might be driving factor loadings that has absolutely nothing to do with the factors whatsoever. And if we're going to assume that, which we can assume, one, you look at the factor, the items, and say like, well, these items seem to be kind of worded similarly, though they're supposed to be tapping into different things. There might be an argument made here for method error, method variance, right? How do we handle that in a factor analysis? Okay, sure, replicate, but we've got one data set and we can't do that right now. If we have error variance that we assume is not related to the factors, what have we done in the past with this? I guess we haven't really had factors in the past, but we have had error variance, and I've said, oh, if we have error variance, then we can do this thing to help control for the fact that it's just plain error variance, if there's nothing we can do about it. Because error variance that's related, correlated error variance, will cause you worse fit if you constrain it to be nothing when there's something there, right? How have we checked for that in the past, and what have we done to fix it? Anybody remember? It's tough to think through this because we haven't done latent variables before, but you can examine your modification indices, and you can make some sort of determination that if a modification indice crosses some threshold, we're going to allow that to vary. Just by chance, you're going to have a whole lot of these vary, right? We saw that one of those factors was accounting for 50% of the variance, like a 50% overlap in variance. That means that a lot of those items are going to have a lot of overlap. If we're going to say that we're going to call something method variance or error variance that's unrelated to the factor, we need to set our threshold, our expectations for what we're willing to free substantially higher than 3.84. There is no rule of thumb, but I can tell you what my rule of thumb is, which I got from Thomas Wills, who is a developmental researcher who did a lot of self-control stuff. And my rule of thumb is 25. If a modification indice says that there is error variance, that adding a single path will drop your chi-square by 25 for 1 degree of freedom, that's enough evidence for me. I iteratively free them, and what you will see in some of these, you'll see this in your homework, that some of those error variances are going to have modification indices in the 200 or 300s, right? That means adding 1 path will drop your chi-square by 200 or 300. That's worth doing, right? That's worth adding. That is error that you don't want in your model. You need to have a good rationale for it. I have some rules that I refuse to break when it comes to this. 1, I refuse to add a path to another latent variable just because of a modification indice. So if I see a significant cross-loading, and the only rationale that I have to add that cross-loading is that it's statistically significant, I won't do it. Because statistical significance just happens, right? Like it happens by chance. And so that's just saying like, oh, this thing just popped by chance, I'm going to throw it in. That's not good. That's not a good enough rationale for me. If you look at the 2 items, and it seems very clearly that these items should be cross-loading because they seem to tap into these 2 things, then that's maybe a different argument. But I think you make the case for it and you present it in your paper or whatever you're doing. Like this item seems to be tapping into or be driven by both of these factors. And if you can make a good argument for it, then and a good argument means you convince other scientists, right? That's what a good argument is, that that's the case, then go for it. Every time I see it, I feel like it's iffy. And it's always post hoc. It's never a priori, right? Yeah, Colleen.
What was the 25 for? Will it increase by 20? We're looking for an increase or
A
a decrease?
decrease, right? We're always trying to minimize chi-square. So when you see a
Squared value?
yeah, yep, that's what those modification indices indicate, is a change in chi-square. It's an approximate change in chi-square. M plus is saying like, hey, if you add this, then I believe your chi-square will drop by X amount. It doesn't always, just FYI. And that's because of maximum likelihood. It's not a straight like, it's not like OLS where you know for sure if you change one thing, it's going to have. It's not an algebraic equation, right? Maximum likelihood isn't. It's calculus. So, all right. We've got our items. We can go back now and we can do a confirmatory factor analysis on this. Before that, I want to do one other thing. I want to look at something that has a ton of items. So let's do the MEAQ, which you guys had this week for homework. Oh, 62. All right, so we're going to look at the MEAQ. We know already from past research that the MEAQ has how many factors? Should be 6. When you guys did your homework, across the homework, there were varying factors from 11 to 6. Some of you made the choice to, that scree plot was kind of crazy looking, right? Like actually there was a dent in on the scree plot where 6 and 7 are almost dead even when it comes to eigenvalues. And then you see a drop off at 8 and then 9 and then 10, but all of those were above a value of 1, right? So the question is, at what point are you willing to stop? Where do you end that threshold? So let's do this. We're going to run this, and bear in mind, the more people you have, the more variance, the more likelihood that you're going to have factor structures greater than, or factor structures that don't map on perfectly. And this is especially true when you have a mixture of overlapping and non-overlapping factors in your model. This is going to take a little bit to run because you've got 62 items and it's got to run all 62 items through 10 different factor structures and then compare those factor structures 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, all the way up to 10. It will compare them all the way up to 10, and spoiler alert, 10 factors is going to be better than 9, right? We could have put in 12, and my guess is that this sample size, 12 factors would be better than 9. We just saw that eigenvalues of going from 1.2 to 0.67 still was significantly better, right? But the eigenvalues just didn't indicate that 4 factors would be better. Come on, you.
Do you remember that last scene in the last Avengers movie where Tony Stark is like building his little thing and he tells Jarvis to like give him that little eigenvalue at the very top? And I was like, what does that even mean? It was like on a structure.
Yeah, I think he just used a word. Yeah. It makes no sense. But yeah, so when he said that, I was like, oh, I know what eigenvalues are, and that's weird that he said that there, but whatever. I think 99% of the population doesn't understand it. And it sounds
fancy.
Yeah. So. So this is taking a while to run. It will take a while to run. Next week we're going to do latent class models, and those also will take a while to run. Because latent class models, it has to work through various classes, compare those classes, and also we set it to do a number of random starts, and so it will run those models over and over and over to try and zero in on the best possible class. So I don't remember it taking this long when I ran this before, but obviously it is taking a while. Is yours done?
Yes.
What the?
I ran it a little faster.
Did you put?
A little
Are you? Oh, okay. Are you using processors? So if you have like multiple processors, you can put processors equals like if you have quad processors, you can put processors equals 4, and it will run it a lot faster. I don't have 4 processors in my MacBook here. Everybody else's is done.
No. I put 12 factors though.
Oh, you put 12 factors? It's gonna run for a while. It's all right. I got all day. Has anybody peeked at your homework for this week? By chance? I will show you just real quick. Let me see if it's. Did I put it here? No. Isn't that a cool looking figure though? By the way. Oh, sorry, don't get to see it. All right. So let's have a look at this EFA. Whoop! I jumped way past it. All right, so we start by looking at our, come on, you. Here's our chi-square for all of our models, right? And one of the things, we can see that even a 10-factor model, the chi-square is significant, and even a 9-factor against 10-factor, we see that there is a pretty steep drop right here, right? With 62 items, what are our known observations? Somebody want to do the math on that quick? Somebody think they can beat me to doing it? Known observations, how many?
So for this particular example, like when we're looking at the formula up there,
Yeah.
I'm just trying to tie it together here. Like would K be 62? Or
Yep.
Okay.
Yeah. So 62 times 63 divided by 2. We have 1953 degrees of freedom or potential degrees of freedom, right? That's a big covariance matrix. Okay. All right. The way that I would think about this is let's have a look at the eigenvalues. So we have eigenvalues that stretch all the way to 10 and are still above 1, right? At 10 we are right here, and then at 11 it drops off. We can go through and we can look at all of the models and see how they fit. But the thing that's really telling for me is this piece right here. We see a drop of chi-square by 4,000 by adding a second factor. A drop by almost 2,000 adding a third factor. A drop of 1,300 adding a fourth factor. A drop of 443 adding a fifth factor. That's not great. A drop of 3,300 adding a sixth factor. And then a drop of only 600 adding a seventh factor. And then they really drop off after that. I might say a 7-factor model, just based on this, a 7-factor model looks best. You don't want to lose out on this, so definitely a 6-factor model looks good. There's a possibility of a 7-factor model. If there's a 7-factor model here, it's inconsistent with theory, unless something else is going on, right? So we know the MEAQ has 6 factors. We've got clearly a 6-factor model. What's going to be our next step? Go ahead, Aaron. What are you going to say?
I was wondering, like, if you made the argument, you end up making the argument you should only have the 6 to get the 3,000 drop.
Mm-hmm.
Is there any issue with the fact that you didn't keep a 600 drop, but you kept a 443 drop? Like, you could have combined the 3,000 and the 400.
No, so the only argument would be like if I move down one more, there's a humongous drop, right? This one, 443, is a big drop. That's a big drop in chi-square. That's not a drop in chi-square for 1 degree of freedom, right? The degrees of freedom change are quite a bit here, right? It's 58 degree of freedom change by going from this factor to the next factor. 58 degrees of freedom is still very significant for 443, but it's nothing compared to this drop. So I think that the rationale here is if I go one more, then I'm going to see a huge improvement in my model, right? This like the improvement of 240 chi-square for 55 degrees of freedom, it's still significant. It's just not what I would say dramatic. And so there are some who would say you need to have, there is this old rule that if you divide your degrees of freedom, or divide your chi-square by your degrees of freedom, that it should at least be greater than 2. That's another rule of thumb, and it's an old rule of thumb in SEM, but it's a rule of thumb, right? If you were to divide 240 by 55, is it greater than 2? Yeah, it's still greater than 2, right? So unfortunately, that rule of thumb doesn't necessarily apply in this case. But so. Anyway, the next thing that we're going to do is what? After we've said, like, okay, I think I'm okay with a 6 or a 7 factor model, what are we going to do? Yeah, let's go look at the fit. So let's just scroll all the way down to the 6 or 7 factor. Which one is this? Here's 6 factors. So if we look at 6 factors, chi-square, we know it's going to be bad. There it is. If we divide that chi-square by that degree of freedom, what do we get? $39.20 divided by 1534, 2.55. I mean, we're getting closer to that 2, but still. RMSEA, are we okay with this? Yeah, that's not bad. CFI? No, that sucks, right? SRMR, it's at 0.03. That's the spot that I want to get to. Let's scroll down here, and let's look at a 7-factor model. Chi-square is going to be significant again. We know that, right? RMSEA looks good. Our CFI now crosses that 0.91 threshold, right? And we know that SRMR is going to be good. I might be thinking 7-factor structure here, but probably not the 7-factor structure that you guys are thinking. Because what I would be guessing is if there's 7 factors, then we have 6 factors of emotional avoidance that are driven by a higher order emotional avoidance factor, right? And that would be the factor structure. So the factor structure would look something like this. And you can't get that from EFA, right? You have to kind of guess at it. But you could make a case for a potential 7-factor structure with items that seem to be cross-loading or very high correlations with one factor and the other 6 factors. Let's have a look at that. So here are our factor correlations. If there is a single higher order factor, does it look like there is possibly a single higher order factor here? I mean, what you're looking for is one factor that seems to be very strongly correlated with every other factor. You think 2? Six is the one I was thinking also. I had to count them down, sorry. The only real issue with 6 is this one, but still there's statistically significant correlations with 6 in all other factors. I think that there is a possibility that 6 is just a higher order factor of some sort, right? So when we can go up, we can look at the factor loadings for 6, and so what I would do is I would go through and compare the significant factor loadings on 6 with all other factors to see if it just looks like it's like every significant factor loading is cross-loading with something else. That would be my guess for factor 6, but I don't know. We're not going to worry about it too much. I just wanted to show you guys this so that you know if you have a large sample with a lot of items, things just get messier, and you wind up having to make a more clear argument for why you think things are the way that they are. FYI, that's what you guys are going to be doing for your homework today. Although it's not so bad, I gave you a smaller, a smaller. Shoot, I might have used alls for your homework. Affect ability scale. That makes me not want to do the next thing that I'm going to. We'll do distress tolerance for the next thing. Okay, so let's do this. Let's put in DTS. Now my input file's not working. All right, let's do DTS 1 through DTS 15. It really bothers me that I did that I had you guys write down those things for alls. Oh well. Oh no, I didn't do it for alls. I did it for the DIRs. Yeah, your homework is DIRs, I believe, right? I'm pretty sure, because I gave you guys actually like. Let's pull up your homework real quick and have a look, just so I make sure I'm not screwing this up. For those who have not looked at the homework, you will get to see it now. Yeah, so the 36 item DIRs, I gave you the actual factor structure, the items down here for each of the 6 factors. Also, yeah, I feel puzzled. I swear to God that I had added this. I must not have saved it. Oh, I'm glad I opened this. Oh, wait. Am I logged in? I am logged in. Okay. Edit. I thought I added this for you guys. I'll add it now, just so you can see it. Because I told you guys that I would try and add these homework for PDF. Yeah. Oh, I bet I did not. Okay, so it's there. Now let's go save. Okay. This is what you guys are going to be testing for your homework this week. Just FYI, it's all in there. Single factor versus 6 factor versus 6 factor with higher order factor structure. So,
I have a question.
yeah, shoot.
In the previous example for the MEAQ,
Yeah.
we were considering 7 factors, right?
Yes.
But the eigenvalues indicated possibly 10.
Yeah.
And I just want to know why in this case we're not really listening to the eigens.
Yeah, so eigenvalues form a piece of what you're going to use for your decision making, right? Ideally, theory forms the main piece of what you're going to make. When you have a lot of people and a lot of items, you will have higher eigenvalues, right? And so you have to kind of nothing in exploratory factor analysis especially offers any type of clear cutoff, right? And so sometimes you have factors that are under an eigenvalue of 1 that you believe should be a factor. Sometimes you'll have factors over an eigenvalue of 1 that you think should not be a factor. And so you've got to be able to make an argument for what you think and why you think it. This is actually why so many measures have so many different factor structures, and you will see like, you know, a reconceptualization of the factor structure of the BIS-BAS, for example. The BIS-BAS, interestingly, is like the most common. This is the behavioral inhibition, behavioral activation scales. It's the most commonly, I think, scale out there for people coming up with new factor structures. And then trying to make an argument based on theory, not based on math, right, for why that factor structure should be the way that it is. And so unfortunately, the math is never clear cut with this, right? And you might collect a sample, you might collect another sample, and the eigenvalues stop at 5, right? And for factor 6, the eigenvalue is below 1. And so it would be nice if it was always clear cut, but it never is. So the question is, how do you know to stop at 7? My primary rationale for stopping at 7 was the dramatic kind of cutoff in that change in chi-square. While it was still significant, it was very clear from eyeballing it that it was different, right? I shouldn't say very clear. It looked different to me. And in a paper, I would say like, hey, I kept going, and it showed this, 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 and this, and here's my rationale of why I went with this. And I think if you're stumbling around in the dark, which is what EFA often is, you've got to have a good rationale for why you're going to do it. Right? So, make sense? Yeah. All right. So back to the alls. Let's run this again. Actually, we don't need to run this again because we've already done it once and we've already identified our items, right? So now what we want to do is we want to do a confirmatory factor analysis of the alls. And we're going to say that there are 3 potential solutions. The first solution is your solution, which says that the alls is comprised of 3 factors, right? And those were the 3 factors that we came up with, and we identified the items that should be loading on each of those 3 factors. The other is that these are all tapping into one single factor, and that emotional instability is not broken up by 3 different types of emotional instability, but just emotional instability. And then the last is that there are 3 factors plus a 4th higher order factor. When you go to test these, what you want to be able to show is that your structure, the chi-square value for your structure, is significantly less, given the degrees of freedom, than the chi-square value of the single factor structure. And when comparing yours to the higher order factor structure, you want to show what?
There's only one higher order factor, so if you have 2 higher order factors, then it should be a bad model.
So there actually should not be bad model fit, right? Because to be honest, that higher order factor structure, go ahead.
It should get like significantly better than the 3 factor.
Yes, if there's a higher order factor, then it should be significantly better than a 3 factor. If it's not, based on the comparison of the 2 chi-squares minus the degrees of freedom, then you can conclude what?
That it is actually
That your model is more parsimonious, and the adding a higher order factor doesn't improve things, right? Yeah. Sorry about that.
To be clear, you don't want the 4 factor structure to be significant.
I mean, what you want ultimately is irrelevant, but yeah, it doesn't matter if it's significant or non-significant. What you really want is that the difference between the two to be non-significant. Yes, I'm sorry, that's what I wanted to say. I think that's what you were actually asking.
Yeah.
So, okay, so let's start by figuring out our own model. So let's type this out the way that let's settle this the usual way. We have use variables of alls 1 through alls 18. That's fine. Analysis is estimator equals MLR. What's the next thing that we type? We're doing just a basic structural equation model now, right? We're going to set the factor structure of this. And just FYI, when we get to structural equation modeling, setting the factor structure is the first step of a large latent variable equation model. And we call this setting the what? Anybody know? The measurement model. So we will have a measurement model and a structural model. And so what we're doing today, right now, is setting the measurement model or testing the measurement model. So what's the next thing I should type here? I'm going to rely on you guys a little bit.
Type.
Type? We don't need to type.
Oh.
But For some we do, but for this we don't. No.
Would you have to create like would you have to create the latent factor or cross it on?
Absolutely we do. And so how do we do that? What's
Say model.
model? Thank you. All right. Model. We've identified that we're going to use maximum likelihood with robust standard errors. We've identified that we are going to use the alls 1 through alls 18. What is the next thing that we do? Name the latent factor. So we have F1 by, somebody help me out, what are the items in F1?
ALS 1, ALS 3, 5, 6, and 7.
On 2.
4, 8, 9, 11, 14.
Is that it? F3.
2, 10, 12, 13, 15 through 18.
Could you do it, just out of curiosity, could you do ALS 15 through ALS 18, or you have to take each one out?
Yeah, you can do that. As long as they're in that order up here, you can. What else do we need to add? Do we need to add the correlations between F1, F2, F3, F1, F3? No, actually, M+ will add those for you. As long as they're exogenous variables, M+ will add them for you. If these were mediator variables, you would have to go and add those in, right? If you had a model that looked like, let's just use these, and it was going to this, and then these here, right? M+ will add that one for you, but it won't add these. So you have to add these yourself, assuming that those are supposed to be correlated, right? And in this case, they definitely should be correlated. Okay, we're still missing something though. What are we missing?
You still have to set one of the full body concepts. So you set the,
Say that again.
you have to set the scaling for the latent factor.
You don't have to. Impulse will do that for you too.
Okay.
If you want though, if you want to set one of these as the scale, you can set it by just doing this. Like if you wanted to change it so that that one is setting the scale, or you can just go like this. Impulse will pick the first one and set that as your scale. We're still missing something. What are we missing?
Between the factors, like F1 and F2 and F3.
No. Help me out. What should I put here? Okay, we could do that. STDYX, not what I wanted, but.
What does that provide again?
What's that?
What does that provide again?
That gives you standardized coefficients.
Okay.
Just FYI, you could actually go F1 at 1, and that would actually remove this as the scaling factor, and it would set F1 to be a standardized variable, and then it would be exactly the same as doing STDYX. Doesn't matter. Come on, we're missing one output that we really need to make sure we have. Yep, yeah, our modification indices, and we usually do 3.84, but I said don't do 3.84. What did I say to use? 25. All right, this looks good. Let's hit run. Let's see what happens. There is our factor structure. It looks pretty good. Scroll down. Let's have a look at our model fit. Just FYI, I have not run this model, so I don't know how it's going to fit. That's a pretty high chi-square. Tell you what, though, that other stuff doesn't look too bad at all, right? Got 0.06, decent confidence intervals, 0.93, 0.94, 0.93. SRMR 0.041. Factor loadings look good. If we come down and look at our standardized factor loadings, these all look pretty good. Why do we get standardized factor loadings for estimate here when we didn't up here? This one is just fixed to 1 and it's all 999. All of a sudden down here, though, we get these. How come our first one is not fixed to 1 down here anymore? Yeah, it fixes our variance to 1, that's right. All of these are z-scores. All of these items look like they're loading very well on the factor that they're supposed to be loading on. Every factor loading is above 0.6 standardized, which is kind of one of the thresholds that we think about when we're talking about confirmatory factor analysis. We want standardized thresholds to be above that. These are pretty high correlations for factors, but what are you going to do? There's our variances that have been fixed. So residual variances. Here's our R squared of our items, who cares? Here are our modification indices. So we have some modification indices that seem, but we have a ton above 25. Do we free all of those? Do we free any of those? Which one? Where do we start? If we iteratively free, and that's how we do this, right? We don't free them all at once. We free one at a time. Each one of these is independent of all of the others, so freeing a bunch at once can cause chaos. We free them one at a time, and if we're going to free one of these, which one are we going to do?
6 with 5.
Yeah, that's the one I would free too. We're not going to add any by statements, right? We're not going to add any cross loadings. That's what these are. It's cross loadings, right? But we've got this right here. That's a ridiculously high correlation, 6 with 5. Should drop our chi-square by 193.
Quick question.
Shoot.
What's the difference between the by and the width?
Yeah, so the width allows a correlated error, right? So when you have a latent variable with these and another latent variable with these, and this is correlated, these are all driving this. And a width says we're going to say that the error of these two things are correlated, right? A by says that's also driving that. That's the thing that I said I don't like to do, right? So I stay away from the by statements, adding the by statements, unless you see a by statement that has a modification indice that is ridiculous. And in that case, I would go and look at the items. And I would say like, hey, this had a modification indice of like 800. And this item sounds like it could be being driven by these two factors, which I've called this, and the item says this, and it sounds like these two factors could both be contributing to your response on that item, right? Anyway, we've added our single correlation here, alls 5 with alls 6. Importantly, alls 5 and alls 6 are also in the same latent variable, right? And so this is another indication that it might be just some sort of error, is if you can say like, hey, look, these two things seem to be also correlated, or these two things are within the same latent variable. So we hit save, we hit run. Anybody remember what our chi-square was last time? We can go back and check it. Somebody write this down for us. We've added one single path, and it should have dropped our chi-square by roughly 200. It was 1100 something before, so I'm guessing it should be around 900. There we go, it is. 947. A chi-square is statistically significant. Our RMSEA is still reasonable, right, where it was before. CFI 0.95, TLI 0.94, both of those look good. SRMR looks good. To be honest, I'm like perfectly satisfied in stopping right here. Let's have a look and see if adding that correlation dropped any of these. It didn't. In fact, these are a little bit stronger than they were before. I feel pretty good about that. Let's look at our modification indices just to make sure. We have a bunch over 25. I don't think that there's a need, though, to add any of those. We already have a good fitting model. There's no need to complicate it by correlating errors that could be correlated because of method variance, they could be correlated because of some higher order factor, or they could be correlated by just dumb random chance, right? And so adding one that had a modification indice close to 200, I think that's good. Going through and now just adding a bunch of random ones is unnecessary. You could do it, especially if you set this a priori value of 25, but I don't think it's necessary. You've got a good fitting model with a nice factor structure. This looks a heck of a lot better even than our EFA did, right, with 3 or 4 factors. So a nice 3-factor structure. Let's write this. Let's take a break. When we come back, we're going to compare these 3 different models.
Show me the code quickly.
Oh, yeah. The code to correlate those is just alls 5 with all 6.
What it, I saw that it also said ALS 5 plus 6. That's like, that's just a correlation.
It said, oh yeah, I'm sorry, yeah.
I think that the other way around, but
Yeah, this is, this you added that correlation, alls 5 with all 6, and it's really the correlated error between alls 5 and all 6. And it is in there, yep. You've added it, it's statistically significant, a Z of 10.
Well, what I was saying was, on the previous, we found out, like, when we looked at the modification of the C's, and it said, like, this correlation is, like, 4 root, like, 193, whatever. Then it said not only 6 with 5, but 5 with 6. So, like, that's just a correlation.
Oh, yeah, yeah.
You can write it.
Either way.
So,
Yeah, either way.
can I
Yep.
see, like,
What's that?
could you go back to the input function?